So to start this quarter, I'm happy to introduce Aaron, who will be speaking on Tamagawa numbers for function fields.
Thank you so much. It's a real pleasure. This is a wonderful topic. So the way I've planned out the talk for today is the first half will be number theory, and the second half will be specific to the problem at hand and mostly topology. There's a lovely sort of rich underlying topological idea behind the argument that is ultimately used by Gaitsgory and Lurie. Without further ado, I'll begin with some really very classical number theory because it relates to almost everything that number theorists have seen of old, going way back to like the Dirichlet class number formula, which is a special case. But so this is what I've called here the Smith-Minkowski-Siegel-Weil formula. I'm just calling it the SMS formula for short because all those names get very tiresome, right? So let Q be an element of some ring R point. By the way, is this good enough sizing for the camera to catch it?
Yes.
Perfect. Homogeneous degree 2, so a quadratic form. Clearly, if M is an element of GL and R, we can act on Q by taking Q M inverse blank. So the space GLNR acts on the space of quadratic homogeneous polynomials. And we say that if Q and Q prime are brought to one another by some correspondence like M, we'll say they are equivalent. And one of the oldest problems in number theory is for a given R and a given N to determine the different equivalence classes of quadratic forms that exist. So very bit of history. The case N equals 2 and R equals Z was initiated by Lagrange, and it's over 50% of Gauss's disquisitiones arithmeticae. I don't know if anyone's ever looked into that. It's a huge theory. And Gauss had a whole theory of more than just sort of equivalence of forms. He also had a theory of what are called genera of forms and a sort of biological taxonomy of these things. And so one of these, the genera actually, the genus of a quadratic form is the one that we're going to be studying with this particular example here. But just as a quick overview of what happens, the answer to this and the tractability as a problem really depends on R. If R is a field, you can always diagonalize it. You can always write it as lambda 1 x1 squared plus lambda r xr squared. If it's complex, if R is C, the complex numbers, this is R a field. If R is C, you can always write it as just x1 squared plus xr squared. So it's determined by one number, R, which is less than or equal to n, the rank. If R equals, thank God for this notation not being, at least it's locally bad, but on the board it's legible. If R is R, it's determined by the signature. You can write it as x1 squared plus xa squared minus xa plus 1 squared minus xa plus b squared. And the difference between the number of positives and number of minuses is called the signature, and it uniquely determines, it and n uniquely determine the type of the form. For R equals QP, and you probably see that I'm being somewhat clever in my choice of rings here. These are non-random samples of rings. It's determined by an element in QP star mod QP star squared called the discriminant. And an element plus or minus 1 called the Hassa invariant. I think we're also assuming here P is not equal to 2. So basically, the other thing you should notice, of course, is that if I have a quadratic form defined over R, I can base change it to any other ring S if there's a map from R to S. So in particular, if I'm asking for solutions of this particular equation, if they exist over R, they'll exist over a base change. So if you want to solve these things, then you can always reduce the problem. This idea does actually go back to Gauss. This is something that's not appreciated. Gauss was the very first person to ask the local principle to ask on page 1, but he never published it because volume 6 volume 6, but he didn't have enough paper and he wanted to save paper, so he never published it. So it's really kind of amazing how yeah, so finally they did publish volume 6. It was like years, decades after Gauss died, so by that time, the other people had similar ideas. But the idea is we can always, we can reduce to simpler rings, maybe like these, which have a sort of continuity in a topology like R and C or QP, and you can determine whether there are, whether two forms are equivalent over the extension rings, and then you ask the question if they're equivalent over sufficiently many extension rings, when can you determine that they're equivalent over the original ring? And this brings us to the idea of the genus. Okay, so let R equal Q at the moment. We'll use a very obvious notation here. We have the following theorem of, so we say, yeah, okay, so this is all to introduce the notion of a genus. We're going to first state a theorem here, which is called the Hasse principle. This is the first sort of success in local principle. Q and Q prime over Q, both over the rational numbers, are quadratic forms. Say are quadratic forms over Q. And I see there's a typo in my notes. So I can actually fix that. Q. Then Q is equivalent. I'll write this. Q is equivalent to Q prime if and only if QR is equivalent to QR prime and QP is equivalent to QP for all P. So this right here is a first example of the local global principle. You check on the completion of every prime of every place in Q, of which there are the standard number. There's all the ways of completing Q. There's the standard p-adic completions plus the completion at infinity, which corresponds to R. And it turns out that if two quadratic forms are equivalent, this is not true for higher degree forms. It's only truly true for quadratics. Are equivalent locally, then they are equivalent globally. So this is the first example of a local global principle. Now we're going to make the problem a little more difficult by asking the same question over Z.
So is that sort of like the simplest description of the equivalence classes over Q?
For genera, yes. So what that means is that if you want to determine yes, sorry, that's right. No, that's right. Because if you want to determine whether two things are equivalent over Q, what you just do is you check over each prime. We now, because of this theorem, have all the means of telling whether it works on each prime. It's a very finite computation. You can work it out. So the theorem is essentially answered for Q in that case. Yeah. Now the same question we should ask about Z. So we can do the same base change, and we will say that Q and Q prime are in the same genus if, well, QR is equivalent to QR prime, and for all n, so we're just going to do it sort of mod n for every single n, Q Z mod nz is equivalent to Q prime Z mod nz. Now, of course, equivalent quadratics are going to be in the same genus, but the converse is not true. Same genus does not imply equivalent. And this leads us to the question: what is the notion of what is a failure? And the answer is there's actually a finite failure. There is a finite number of quadratics in a single genus up to equivalence. Is the handwriting still good, Nikolai? Is it still legible on the?
Slightly bigger, possible.
All right, we will enhance. But yes, so it's essentially a finite failure. So I'll just introduce some slight notation here, and then we'll get to that. Now, the Smith-Minkowski-Siegel mass formula basically gives you an an estimate on the size of how big a size of genus is for a given quadratic question.
So is it equivalent to just say that QZP is equivalent to Q prime ZP for all P?
In fact, yeah, it's Z hat times R. We haven't yet introduced the Adels, but those are coming in. Those are coming in two. Yes. So what we're going to do is we're going to view Q as a function from the lattice lambda n to Z. Observe that this form Vxy, which is defined to be Qx plus y minus Qx minus Qy, is bilinear. This is just true for all quadratic equations. This kills off the naked quadratic terms. So this therefore such a Q induces a map which we'll call rho from lambda n to pom lambda n z. Which we'll define as to be lambda check. Okay, which is x max to ex blank. And let's see here, I'm just going to give you some notation. If the quadratic itself is defined over Z, it's called even, because it turns out that Bxx will always equal to Q, will equal to 2Qx. So this is always with an even values on x-axis. Question.
Sir, is lambda like an n-dimensional x?
Lambda is an n-dimensional. Yes, lambda is. I'm sorry. Actually, I'm using my lambda is going to be Z at the end. Thank you. I mixed two notations. Yeah. So imagine evaluating only on the integer points, the x-axis. And so now we're rushing through the notation here. So this is called but yes, we're trying to get to the actual theorem here, just how big this, size of the set of quadratics of a given genus is. So let Q be Q and lambda be uneven. Positive definite. So when I say positive definite, that means when I base change to R, it's positive definite. Then the following is our theorem. I think that we've exhausted all the theorem, and this is the SMS theorem. Failed to mention anything. No, I think this is all correct. All right, so Q prime equivalent. So let's make the same genus. I'm going to introduce a new notation. There's one other piece of notation I need to introduce. Of course, there would be, which is I described finally. So the last thing I'll introduce is the notation of the orthogonal group with respect to Q. These are the automorphisms of the lattice that preserve the quadratic form. Okay. So here we have this wonderful theorem in number theory. So if we sum over all the quadratics in the same genus as Q, where we sort of count each up to 1 over the size of its automorphism, this is going to be given by a formula that reads as follows. It's equal to 2 times the. So you can see, by the way, that rho is injective. And therefore, there in fact will be a finite quotient of lambda check mod lambda. So this is a finite number here, assuming it's non-degenerate. I should probably add non-degenerate, even positive definite, non-degenerate. So that's to say that this quotient is finite. And this 1 over 2, and we're going to run out of space, but okay. Divided by the product m equals 1 to n times the volume of the m minus 1 sphere, plotted over p CP.
What is the exponent, n plus one?
That is n plus 1 over 2, yeah, n plus 1 over 2, yeah, sorry. And by the way, this is famously, notoriously difficult, a lot of people make like a lot of errors in writing this formula down. Conway and Sloan are the most reliable source for this because they actually check their computations every single time with a computer. So if you ever want to see this done properly, you definitely want to outsource to as much, computational power as possible. And so, where this is the volume of the m minus 1 sphere under standard embedding, and CP is going to be a kind of local factor in terms of p, which is equal to 2 times p. Now this is an interesting point about the proof, about the statement here, rather. There's n minus 1 over 2 over for every sufficiently large k. So I apologize for the slight awkward grammar. We do need to pick a single k and then stick with that k for all the p's. And you can't make k be too low, but once you've picked a sufficiently large k, every k bigger than that, we'll change each factor here, but their total product will be independent of k for sufficiently large k.
Do you need the numerator of this?
Yes, that changes the numerator of the CP here.
Because I cannot.
Oh, sorry, is this too small? That's p to the k.
The numerator.
Numerator, so.
Let's see here, sorry, it's 4, so that's k and n minus 1 over 2. Over z mod p to the k z.
And k is what?
K is some number, is some integer you have to pick, and it needs to be sufficiently large. But then once you've picked it, provided you stick with it for every single factor, it will give you the same product, which will be the ratio of this to this. So a couple of points, n times n minus 1 over 2, that's a dimension of an orthogonal group. The extra 2's that keep appearing are because there's a difference between O and SO, between orthogonal and special orthogonals. There's a twofold symmetry. So you're gonna see this also has a kind of like topological flair to it. This is like a fundamental group. So you can see here that what we have is, and this right here is the sort of famous, we've seen this before where you're trying to count the number of points on a stack. You always divide by the size of the residual germ to compute its mass rather than a sort of standard point count. So there's some kind of stacky computation of points going on here, and we end up writing it as a product in terms of these local factors in P. Question.
So is k dependent on q?
The size of k is dependent on q, but once you've picked a specific one, it can be sufficiently large. Any sufficiently large k will do. So, sorry for writing. It was actually very confusing the way it was written in Lurie too. Of course, this number will not. This individual factor CP is not independent of k, nor does it stabilize as k gets big. But the whole product does once you've chosen sufficient. And I think that the bound. So I will mention a couple of things here.
Should the sum be over q primes?
Yes, thank you. Yes, you don't want to just be doing Q. I mean, Q will be one of them soon, presumably, because Q is equivalent to itself, but it's only one. So you can actually pick k equals 1 if p does not divide. If p does not divide these are the sort of bad crimes. If p divides the sort of fundamental group here. So in particular, if this equals 1. So-called unimodular lattice case, you can let k equal 1 and you can do a slightly more simple formula, which is probably how you've seen it. And I'll quickly write that up, and I'm going to move on from this, which is, if lambda check equals lambda, well, firstly, that can only occur in the situation.
So if p does not divide this, then what?
Oh, sorry, if p does not, then you can get k equals 1.
That makes sense though, right? Because k is supposed to be uniform overall.
Sure, so let's say, you want, so yeah, if lambda check over lambda equals 1, you can let k equal 1. There we go. I think that's the right way to say that. It can be slightly stronger in that, you basically want to exclude, you want K to be bigger than any of the prime divisors of this. So that's the bad stuff, is it?
So if P does not divide quotient, for example, the quotient, it's still, the CP can still not be equal to 1.
Yeah, yeah. I guess there's probably some kind of subtlety about, maybe there's some extra subtlety in the specific choice of K, but yeah, this is just to make it technically correct. I don't want to say something stronger because of course, you're right, you want to peak uniformly for K. And so if indeed there is a K that divides, if there is some prime divisor, you need to make it bigger, that doesn't, yeah, you need to make K sufficiently large that it doesn't have any sort of division of this bad number.
I'm sorry, so the left-hand side is just the number of isomorphism classes in the genus.
Counted up to their automorphisms. So this is always going to be smaller than the number of isomorphism classes because that's like a 1 over n. So this gives you a lower, let's see, it gives you a, yeah, it gives you a, so it gives you a lower bound on the number of isomorphism classes, right? Because whereas you'd be summing 1 for each isomorphic class or something 1 over its work. But it does show you that there's only finitely many in particular. Well, that's not necessarily true. It could be an infinite sum. So, but there are only finitely many. This is a finite sum. The finite sum. That is actually a theorem. So if lambda check equals lambda, this is the more famous version of the formula. This is called a unimodular lattice. I'll say this is then 8 divides n necessarily. You will never have a unimodular lattice outside a dimension divisible by 8. Then you can actually group the terms together of this expansion and you get all right. Theta 2. Theta 4. Theta n minus 4. Zeta and 2 all over volume of S naught times volume of S1 up to volume of S n minus 1, which can also be written as all right. So if you have a unimodular lattice, then firstly, these annoying factors at the beginning become much simpler, or that annoying factor on top certainly becomes simpler. But you can also lump together the p's in families, and you can actually write this as you can therefore write these as the Euler products for special values of zeta. So this is one of the examples in which you see special values of zeta are intimately related to the kind of mass of the genus, the kind of, when I say mass, I mean the number counting for automorphisms. So there's a whole deep set of relationships in number theory between special values of zeta and Tamagawa numbers, which is what this turned out to be. A quick little mention of the consequence for this. This formula immediately allows you to see that basically in the case of dimension 8, there's only a unique unimodular lattice, and that is E8. In the case of dimension 16, there are 2 unimodular lattices, E8 times E8, and one other one which has a root system that's dihedral. I wrote out the formula in the notes, but I won't write it up here because it just will take too much hand power. In 24, there are 24 unimodular lattices, the most famous being the huge lattice, which would account for a very, very small amount of mass here, which is the Leach lattice, which is the most symmetric by far. And then actually for 32, this number begins to explode. There are over 80 million different unimodular lattices using the obvious bound here. So we know that there's just way too many lattices for us to actually classify them. So, but for 24, they're all called the Niemann lattices, and they're all fully classified. You can read Conway's Splag if you want to see them. And just a little bit of history. in the case of n equals 2, this actually, this SMS formula actually reduces to the class number formula of Dirichlet. You need to recognize that one of the sides is the class number of the quadratic, but it's maybe not so surprising if you begin to think of this as a kind of local global principle, because that is what a class number, in the modern cohomological version is thought of as. Eisenstein gave some partial results, and actually Smith himself, he discovered this formula in 1867, and his work was forgotten. So it was Minkowski who rediscovered it with some errors, and then those were corrected by Siegel in like 1935. So it took a really long time to get this formula right, and then finally, 1964, 1965. They extended it. There's a more deep formula involving sums of Eisenstein series, which this is the constant term, and that's the full formula, but I haven't written that one out. All right, so we're going to now interpret this. Question, sorry.
So how would you use this to figure out that there are only like finitely many unimodular lattices? Because it seems like we start with the unimodular lattice and then we get some statement about forms acting on that lattice, but it isn't.
Well, so it certainly gives you a lower bound for the number of different lattices. So in theory, this could be an infinite sum, right, which just converges.
But doesn't it just give us a lower bound for the number of quadratic forms on that lattice?
Of the same genus, yeah, because you can bound this by one. So it gives you. So sorry, is your question? Do you want an upper bound, or is it? I feel like I'm probably missing your question here.
So it seems like we have like.
With choice.
Oh, okay.
Yes. No, this is important. So you need to pick a Q, and then again, you need to pick a lattice with a big quadratic form, and then it will tell you how many lattices there are in the same genus as Q.
Okay.
Yeah. Does that make sense?
Yeah.
Yeah. So it tells you not to sort of tell you how many weighted, right? How symmetric each. More symmetric, the less it becomes.
Still not clear to me, why then the right-hand side and left-hand side is finite set.
No, it's not. That's a separate theorem. It's not. And in fact, in the cases that we're going to be studying, it actually won't be. You can absolutely get cases in which you compute a Tamagawa number, and it's like an actually infinite sum, and convergence becomes a real issue at that point. The series that you study.
So the denominator there has a bunch of like pi's, right?
Yes, that's right.
So those get canceled by this product of those. So
That is correct, and that's why it's an irrational number. That's actually a hugely important thing. Those relate to like these rationality conjectures of Bayesian, and then the Bloch-Kato conjecture gives you the specific rational number that it actually has to equal.
the CP is like an Euler product.
Yeah, it's a sort of amalgamation of various. Yeah, you can imagine, right? Because imagine the formula for the orthogonal group size, right? It's going to be like q to the n minus some q to the n minus products of q to the n minus 2 to the n, right? Divided by some other q to the n minus 2 to the n. Any other questions, thoughts, comments? I hope that the theorem itself is not too confusing. It's slightly confusing the way I've written it. I do apologize. The K dependence is extremely irritating. But that's having to deal with bad primes is the bane of every number theorist's existence. Okay, so now we're going to interpret this delicately. There's a wonderful quote of Jim Arthur that Adels make life possible, and I have to say I really agree. So Q and Q prime are, is this big enough that the camera can see? Maybe I make it bigger. Q and Q prime are in the same genus if they're equivalent mod n for each n, and if they're equivalent over R. Well, you can see lies, and it's in fact that Q, so Q z hat times R is actually equivalent to Q prime z hat. Okay. This is by definition, because it means that it's their equivalent mod each z mod n. Now that there's a little bit more to check. I need to check if they're somehow compatible to glue them into something like this. That follows by a pretty simple lifting lemma style argument that I won't get into. But it actually turns out that this is biconditional.
Your convention is always that the twiddle stands for same.
Yeah, twiddle means same genus. It's a term that I adopt. I'll write it here. Same genus. See, as I say, it's this biological classification. This is domain, kingdom, phylum, class, genus. This right here is actual equivalence. And of course, Z hat, I should just mention, is the pro-finite completion. See. Now, we also know that Q and Q prime are in the same genus implies that I'm probably getting something slightly wrong. I think this is probably true, but I'm going to erase this by conditional. This is certainly true. You do need to make them compatible. This is certainly true. There's a slight thing to check here. You do need to make them compatible, but it is true that if they're equivalent mod each n and they're equivalent over R, you can actually sort of make these equivalences compatible with one another, which is the content of this statement. I'm not going to make it biconditional quite yet. The other point is we know that by the Hasse principle that if Q and Q prime are in the same genus, then they're also equivalent over Q. For this reason, let's actually be a bit more specific, and let's call this alpha. Let's call this particular equivalence beta. So alpha is in GLN Z hat times R, and beta is in GLN Q. What we find is beta inverse alpha is a well-defined element of the following double quotient of sorry, when I say actually beta, yeah. Okay. Mod OQ A mod OQ Z hat times. So now this is the one that I want to be biconditional about. So it turns out if you give me the sort of equivalence over the finite adels, and you give me the equivalence on the rationals, then I can actually reglue those two equivalences together to get exactly a unique genus representative of the a unique element, a unique genus class of quadratic forms. So this is biconditional. So again, I'm now introduced the adels here. The adels, I should just define them quickly, are the restricted product over all completions of all places, B place of Q. And you can see that it's actually equal to sort of within, this is an internal to the adel, so you need to know this in advance, but this is equal to Q times the Z hat times, which is sort of why this is the adels are sort of the minimal thing that will contain this. And that's why you need this. That's the natural place for B inverse for B inverse alpha to live. It's valued in the adels. So claim. Set of Q prime equivalent to Q of Q prime equivalence Q prime equivalent to Q modulo actual equivalence is, there's so many different squiggles here, but this is automorphic to this adelic double quotient to OQ A OQ Z hat. So what does that mean? I actually mean not only that there's a bijection, not only that if you give me an element of this double coset space, I can reconstruct an element of the genus, the quadratic form. It means that in fact these are equivalent as groupoids too. That is to say, there's an extra stabilizer given by the double quotienting action here, and that will exactly agree with the automorphism of Q prime here. If there's an element, Q prime will correspond to some element in here, and it will have some, it'll actually be, it won't just be a sort of point, it'll actually be a point mod some group, some finite group, and that will actually agree. So this is equivalent as groupoids. And yes, with this we can just mention briefly, and I think this is the last on this sigma gamma element of I don't know what to call this. Let's call this M. You can slightly reinterpret the sum, the mass there, by sort of the orbit stabilizer theorem to be this kind of this intersection. So you can interpret the group in terms of this double quotient here. And so the actually automorphism here actually equals this automorphism. If gamma corresponds to Q prime. So it's actually, this is a term-wise equality of the sums, but of course their totals are equal as well. So that this implies. That's the implication that we want there. And it's sometimes easier to work with this form of the Siegel map of the Tamagawa number than this form thing, basically. So yeah, so now I'll have a 2-minute interlude on stacks. Later. So claim yeah, sorry, before I get to this claim, I want to do one little thing. So interlude. Consider the quotient stack x minus g, x mod g, mod the action of g, g is some group acting on a variety x. I do mean stack. The reason that you end up counting 1 over the automorphism of each point is that it actually makes a far nicer equation for the sort of total count, as it were, total mass of x mod g. What you find in this case when you count properly, by which I mean you count 1 over the order of the residual gerb at each point for a mass computation, the order of x mod g, the size of, say, the fq points of x mod g as the stack, will actually equal fq mod g fq, which is very pleasant, where we define this. This is defined to be the sum of each rational point of the stack. See how I wrote it out here, because we want to have to build a little bit of notation. Sum of stack u to x. It's called stack. Put in the x for x mod g. Absolute sense. Okay. So we define the mass of the stack this way by looking at all the FQ points of the stack and then dividing by the order of the residual term. And if we do that, then it turns out that this is a theorem that will just equal exactly the quotient of the two spaces. So this is very pleasant when you really want this. And this is why in counting points on stacks, this is the correct and natural way to do things, rather than just say counting one for each point. I'm sorry for the terrible notation here. This has sort of been a little bit covered before, but I thought it was mentioned explicitly. In our case, what we see that this sort of means for the idyllic case is that we see that the following is at least plausible, sort of applying this kind of statement here. In the case of a finite set, this is just orbit stabilized. If I count each point 1 over its stabilizer, this is going to, of course, be exactly the total number of points divided by the orbit of the active. So this is just a very fancy, stacky way of talking about orbit stabilizer. So in our case, when we're dealing with the sort of this kind of a formula, we're dealing with some sum like this. What that means is we should expect this to be some kind of a ratio of volumes, right? This is a double quotient that we found here, and we're counting each point up to its individual stabilizer. So it should be some kind of total double quotient, and indeed it is. So it's OQZ is equal to the So you can see that this is sort of very much an analog of this kind of thing. You have a double quotient, so we're only quotienting out by 1 here, and then we're dividing by the volume of the OQ's integral Adele points with the Archimedean in place, and this should equal the sort of total mass of this groupoid. Now, of course, if you actually want to make this rigorous, you have to unpack both sides, and what you'll find is that this is exactly a restatement of the SMS formula. In order to make sense of these volumes, you need to go place by place and give me a volume for each term, and you'll end up seeing that you'll get each term counting for, this will be the correct volume when you made it all correct, when you've done it all correctly, and you'll see that this will actually be precisely. This is just an idyllic reformulation, an idyllic repackaging of the Smith-Minkowski-Siegel mass formula. So at the level of, when you interpret it this way, it's very, very plausible and sort of intuitive that this should be the case because it's simply a ratio of volumes of particular double quotients. So any questions on that?
So it's kind of.
Yeah, I should say mu is a. So this is an open set inside the Adele. So let's say a Lefschetz measure. This is for good groups. This is it's unimodular, but Lefschetz measure on the idyllic points of Q. Okay. Now, one point about number theory that's worth bringing up when you're dealing with Z and Q. This famously is discrete inside of this. OQ is actually discrete inside the idyllic points. That you will not find in the function field case. We'll have an analogous sort of theorem, something similar to this, at least, I don't know how far the analogy can be taken, but you'll end up finding that basically this space, the space of rational functions, is contractible. So it's not discrete inside of the space. It is, though it is, interestingly enough, it's very topologically trivial, and that's going to be extremely important to our argument. So this actually is these are both finite measurable quantities, and if you unpack what they actually equal by going through having worked out what the Lefschetz measure is, of course, it doesn't matter which one you pick, because if I chose a multiple, it would just cancel top and bottom. So it's the ratio of these two volumes, and you can work out that it will be exact recovery of the Smith-Siegel mass.
It's discrete and co-compact.
So discrete, and I'm pretty sure co-compact.
Otherwise,
Yeah.
the measure.
Otherwise, it's hard. Okay, I think that's true. I had a little bit. I wrote that in my notes and then took it out because I got terrible cold feet when I realized the upper half plane fundamental domain isn't compact unless you add the cusp at infinity. You might be right though, but anyway, there's a 1 over y squared that makes that whole integral converge. Anyway, we'll now the last thing we'll do before I send everyone out on break is we'll state the actual Bay Tamagawa number.
Does it make sense to consider the mass of the right quotient? You took the left quotient here, like OQ mod.
OQ mod A mod. don't believe so, because this would have mass 0. This is discrete inside. Right? This is actually, yeah. So, okay, now. We're only a little bit behind, but we'll get you out, at least knowing what this whole quarter is gonna be about.
But was the statement just that this quotient is in fact compact?
Yeah, so I think that in fact this is compact and therefore has finite hard measure, right? That's one of these main theorems in number theory that sort of generalizes all the discreteness and then the co-compactness, and I'm pretty sure you're right, Justin, I'm pretty sure you're right, it had. But I did get cold feet in writing it in, but the discreteness and co-compactness is something that is massive generalization of if you do it for GM, that already implies the finiteness of the class number, the finiteness of the class number, the zero play unit theorem,
the group OQ enters, right? I mean, it's not like an F online or something.
That's true. So if OQ were to equal GM theoretically, this is the general theory is if you have a reductive group and you consider the rational points mod the adelic points mod the rational points, then it needs to be semi-simple reductive, I think, actually, to make this work. Then it's discrete and co-compact, and that is a large generalization of the sort of standard theorems of number theory and sort of packaged in the adelic way. Okay, so I hope this sort of gives a here of what's going to happen. So now we get to the main theorem. So let G be semi-simple algebraic group. K of global fields. So an extension of Q, or of a function field in one variable, or function field in one variable. Choose for each E in places of K, a R measure on KV such that one measure, let's call it mu V of OV is equal to 1 for almost all V, and 2, mu of the additive quotient product for all V, mu of KV mu of del's on the rational points is equal to 1 there. Mu is the product over all places. Okay, so you might want to just make them all 1 here for these, but that doesn't necessarily work. That might not get you this. You might not be able to simultaneously satisfy. So what you do is you'll mix it up at a finite number of places. So that this is always equal to 1, but only a finite number of places. That's alternated by sort of rational numbers. Okay. Some finite quadratic powers of P in the case of the rational numbers. So we're going to pick these mu V's on each KB in this way. Let n equal the dimension of G. And now we're going to pick omega W, a left invariant n form on GK, on the rational. It's very important this is a rational top form on the rational points of GK. This gives a top form on GKB for all B. Together with the mu sub v, this gives a Haar measure on GK. Multiply these together. Gives a measure mu on the adelic points. And we will call this mu sub Tamagawa. So it's important that you're you pick these carefully, slightly carefully, and then you pick a rational top form. These give you a rational top, these give you top forms over each completion. And now this gives you a measure, that gives you in turn a measure on the v-adic points of G for every V. And the product of all these two measures. This is all to come up with a sort of canonical measure on the adelic points. Now, notice if I chose a different omega, this would be changed by a rational multiple, an element of k. And that means by the product formula that this wouldn't change. Similarly, if I screw up a finite number of these, I'm only changing things by a rational number, the product formula would also carry the thing. And this is actually a canonical measure. And it looks like I made lots of choices, but this is actually a fully canonical measure. Now we can state a theorem. Definition. The Tamagawa number of a group G is mu sub tom of this quotient of the adels by the rational points. So I haven't written it on the board, but of course implicit in this is the notion that this in fact, for say a reductive group or nice algebraic groups, this is actually by invariant, therefore it descends to the quotient, so it's a perfectly meaning quotient. Of course, this is also discrete, so this will be you can therefore descend very simply to the quotient here. Of course, there's also the implicit statement that this is finite mass. This is actually a finite number. I mean, it's possible, in theory, the Tamagawa number will just be infinite. You just call it infinity. But this is called the Tamagawa number. Now, this, of course, this space here is automorphic space. This is the most important thing in number theory, which is the sort of adelic points of G modulo the rational points, and it's the L2 space of functions on that you study automorphic forms. This is everything. So this is sort of the volume of the most important space. And here is the theorem, conjectured by Bay, who computed it in several cases, and proven by a mixture of, for number fields, by a mixture of Langlands, his student Lai, and Kottwitz, modulo some sort of technical considerations. They proved it for basically everything that was not E8, that didn't have any E8 factors, and then the final sort of technical property of E8 was demonstrated a few years later by Chernousov. So this is a whole bunch of names. I won't write them up because it'll take too much time. But this is Bayes. And then, of course, for function fields, it was done by Gaitsgory and Lurie. It's not confused with the Bay conjectures. Let G be a simply connected. This is the most important assumption. Like unimodularity. I'm going to kill off that I1 term. Semi-simple. Tamagawa number is almost always denoted tau G. Yes. Then tau G is 1. All right, so in the 1 minute before I let you off, this of course sounds really kind of unexciting if that's the case. And that would mean that this numerator that I was just erasing is 1. Although this is not actually simply connected, it would be like a power of 2, so it would be related to the order of the group. So if you did SO, it would be simply connected as opposed to O. But just so you give a little bit of a sense of how tricky this formula is. This, it's one of these things. It's a bit like Stokes's theorem. It actually this tiny this simple equation contains such vast multitudes within it that it's more than meets the eye. So the example here is G equals
Then
SO.
you said that SO is simply connected, so is this understood over the reals then only?
So no, good point. Simply connected in the algebraic sense. So the weight lattice equals the character lattice, right?
So then SO is not simply connected. Yeah, then the spin cover, right?
You're right. Sorry. No, that's right. It's true for spin. It's true for spin. It's not true for SO, nor is it true for O. O isn't even connected, right? So yes, no, very good catch there. Yeah. No, so what happened was actually one of the earliest computations we did for SO, and they found it was wrong, and they found that it was therefore true for the spin cover, and that's what I think led Andre Bay to conjecture this. But let's just very quickly give the example of you need to compute therefore the measure of SLN Q mod SLN AQ with respect to the Tamagawa number. Now I've written it up in my notes, but you're going to have to trust me that mu p of SLN ZP is the product y equals 2 to n of 1 minus p to the minus I. When you actually do all the normalizations correctly, that's what it turns out to equal. This is a bit like the order of SL2 FP, but you divide it by a large power of p. It's originally p to the n minus 1 times p to the n minus p to the n minus 2, all the way down to p to the n minus p to the n minus 1. You just divide that by p to the n squared, basically, and you get this. The reason you have to divide by p to the n squared is because, or more or less, the Lie algebra is almost sort of dimension n squared. It's SLN is actually dimension n squared minus 1, but I'm being very hand-wavy. The computation is done. It'll just take too long to go through here. What does this mean then, if you were to take the Tamagawa number conjecture? Tamagawa number. We have mu of SLN Q mod SLN AQ is equal to mu infinity SLN. This is from the so-called strong approximation theorem times so breaking it up into its Spartanian and non-Archimedean components. Well, we see the Tamagawa number equaling 1 is equivalent to the following amazing theorem. And then I'll let you all thought here, which is this term right here is going to be inverted to give me, if the product of this and this equals 1, then this is the inverse of this, which means I get 1 over 1 minus p to the minus I. Those are all the Euler factors of the Riemann zeta function. Z is the classic Riemann zeta function. So this right here is the Tamagawa number for SLN. And you can see that this is highly non-trivial. I mean, even think about the case of 2. Is it obvious that SL2R mod SL2Z has a volume that's pi squared over 6? It's plausible if you think about the volume of the SL2R mod O2R. it gives you an extra factor, that gives you the upper half plane, with its famous hyperbolic metric. The volume of that's pi over 3, and you get an extra pi from the O, and so an extra 2 because it's O versus SO. So very hand wavy argument, but that's how you get the pi squared over 6 if you want to see it sort of very, very hand wavy. But even just convince yourself for 2. Now, there's a lovely paper by Paul Garrett that goes through this proof of this particular case in full detail. To prove it, you actually end up doing some Fourier analysis. Langlands came up with a general method that accomplished this in several other cases. But the numbers 2 through n are related to the actual topology, to the sort of the homology of the group SLN. They're a bit like the exponents in some sense. They're not exactly the exponents. You need to change them up, but yeah, it's an interesting thing. So you can see your special values of zeta, an actual arithmetic group quotient, its volume is related. All these things are sort of encapsulated by this Tamagawa number equals 1, so economically and beautifully. So all right, so break time. Sorry for keeping you. All right, so I'm going to try to cover as much of a general sort of picture of what goes into the computations for the number field, for the function field case, sorry. And so let me quickly find where we was wrong. I scrolled and then lost my place. Okay, yes. So the first thing we're going to do is we have to remind ourselves of our favorite player. This is the BunG seminar, and so far there's been a remarkable absence of BunG in my talk. So I'm going to quickly, very, very briefly remind everyone that BunG is just around the corner here. So recall that as a stack, in fact, when properly interpreted, you can make sense of this in full. But these are certainly true of, say, the points and residual gerbs of the stack. G for integral adels. A AX. This is very, very similar to the argument done for the quadratics. The adelic double quotient equaling BunG is basically because you can generically trivialize the G torsor, and you can and you can trivialize over each formal disk. And so putting it all together, it's a uniformization theorem. Tom gave a talk 2 quarters ago on this, and you can watch the video, and that's where that's even more difficult than this, because that's involving just sort of 1-point magnifications.
And this is where Justin will say G is semi-simple.
Yes, I probably do, don't I?
Wait, sorry.
No, I know. I think this is true.
No, it's no, you don't. This is true.
No, this is G is semi-simple is if you remove 1 point. The 1 point magnification is only
sorry.
G is semi-simple. Yeah. No, this is true always. Yeah. Yeah. Okay. Great. So now, of course, this is a geometric object. We can think about this. There's a lot of geometry we've discussed. We hope to use the geometry of BunG to derive information about Tamagawa numbers. This is something you couldn't do in the same way in the number field case, at least not with our present technology. They do it, in fact, in great generality. They say let G equal having to X be a reductive group C. Consider E is equal to the dimension G. Consider the relative cotangent bundle and its top form. And consider the pullback of this. L. I'm doing the terrible thing that I would always get frustrated when I pre-write my thing in order to be more efficient in my voice work. But let L be the pullback along this map E of the top exterior power of the relative cotangent G over X, where E mapping X to G is the identity section. So now you have a grammatical statement that you can parse. We're going to pick, this is all analogous, we're trying to construct the Tamagawa measure here to understand this. Pick omega in L, a rational section.
Do you require G to be like constant locally?
No, but you do require it to be reductive. You do require it to be as a relative group scheme that's reductive, as is so far at the moment. I think actually prove it in full generality of this kind, right, Justin? I think it is actually in full, but it's still true for a semi-simple group scheme. It's still true that this, so there's another example of which, it's probably outperforms the number field case. Okay. I'm going to tell you what the Tamagawa number is. Had we done the computation last time, you would have been persuaded by this, because you're dividing again by the power of q. GOX is q to the minus degree x v x omega times the order of GAX over kappa x. Okay, so what does this say? If I take my Tamagawa number, my local Tamagawa measure of the formal disk value points of G, it is going to be the size of the residue field of G divided by this particular power of the size of the residue field times extra factor of Q, which is the equivalent to the sort of normalizing factor to get everything to map to 1. This is to get everything to be as sort of defined in my original case. We'll go through the computation that will convince you that this is the correct measure in a second. But that actually turns out to be the local Tamagawa number. And you can just take that as a definition if you want. As I say, had we done a previous case for just SL2, SLNQ, you would probably be persuaded that this is more or less correct. Okay, so now let G naught be a semi-simple algebraic group over KX. Define the Tamagawa number, define the Tamagawa measure. Q d to the 1 minus Q to the power of d times 1 minus G i.e. This is going to imply immediately the Tamagawa measure of the integral adels, value points of P and A. Adels. I probably use assistive notation. My apologies. Is Q to the D 1 minus the genus of the curve minus the degree of the line bundle. That's amalgamating together all of these times. Can everyone see, or is it too bad? I'm writing too bad here at the bottom. Is it getting too constrained? Okay. I really apologize for these multiple line things. I just ran out of space with these long products, and this whole talk is about products of various kinds. So we're just going to be running out of space and having to creatively indent G X over by the way, so when I write x as an element of x, I mean over all closed points of x. X is a curve defined over Q. I should have mentioned this. So It's so second nature at this point to write X as the curve that I forgot to even define it. So for those of you who are new to the seminar, that's one of the conventions that we have. X is the curve over FQ, and K is its function field. This double quotient is BunG X. Now you consider this relative group scheme. We have this line bundle, this rational section of this line bundle. We use it to cook up this Tamagawa number, this Tamagawa measure on each local place, on each local completion. We multiply them together to get this formula. That's just, I'm sorry that it's so bad. These are 2 lines. But yes, there's this factor, this extra Q factor, and then it's sort of G kx, the number of kx value points in the residual field X, which is the same thing as Gauss reduction, mod M, modular maximal ideal, divided by the dth power of the size of the residue field. What happened to the second in the power of Q? Second term in the power of
The Q to like the exponent.
well, when you amalgamate these together, right, this will become deg x times bx omega. And omega has been chosen to be basically this a section of the relative cotangent sheaf. So when you take it, it's just the degree of the it's just the degree of L line 1.
Oh, this is the degree.
Yeah, so sorry, that's when you amalgamate them all together. All right, so back over to the front.
I guess if G is constant, everything to do with this omega is gonna be trivial, right? It's.
Yeah, so that's what I was saying, but that's maybe an EG. Let me quickly see that I'm not stomping on my later thing when I made this reduction. Right, well, yes, okay, so yes, you're right, if G is constant, that is totally trivial, so I'm not actually saying anything of interest. But yes, okay, so, but okay, let's do the example here, let G equal GA. Okay, so then dim D equals 1, L is isomorphic to OX. Absolute value of GK X is the absolute value of kappa X. For all X in X, closed points of the curve. Then, so. The integral Liddell's, the Tamagawa number, measure of the integral Liddell's, is simply Q to the 1 minus G. Now, there's this old Weil exact sequence, which I'm going to write in a slightly fancier way here, but I'm going to be using the terms that we have. We have the exact sequence. Always, exact sequences are like products, that is to say, you run out of space on the board. Question?
I'm sorry, what is that? There's like equals kappa X for all X and X, what is the left hand side?
That is the number of points in G kappa X. It's the affine line. It's A1 over kappa X. The number of points is, because it's GA is the example of G that we're doing here.
Oh, okay.
Yeah, sorry. It was this is an example just to show, just do a little computation to make sure it all sort of works. And so we have this exact sequence, which is just the Weil exact sequence, stockwise, Zariski stockwise exact sequence, standard sort of sheaf cohomology. And we get, from this, we find that the Tamagawa number of GA is the H1 of X OX divided by H0 of X OX times mu Tamagawa of A0 of the integral dells, Tamagawa number of the integral dells. I'm using this because that's the same thing as the G of the integral dells, because G is GA right here. So, and we see from above that that is Q to the G. We see from just standard sort of algebraic geometry, this is Q to the G over Q times q to the 1 minus g. Okay, so this is 1. So it's been rigged, actually. That extra factor has been specially rigged so that GA is 1. It's exactly the same condition that we had the original definition of the Tamagawa number, where we insisted that that A mod K have total mass 1. So this is very important to make everything work. It also means that under Vein restriction, the Tamagawa number behaves well. So this right here gives you a little computation to see that the regularizations that I put in all make sense. So of course, we have the Tamagawa number conjecture that if G is Theorem. So that's our conjecture, which we hope. So we made sure everything's regularized. Of course, GA is not a reductive group, so this is not an example of this conjecture at all. But you really want to rig it so that GA has the Tamagawa number 1, or else the whole theorem doesn't work in the Tamagawa number 1. So
Semi-simple, simply.
say again.
Semi-simple, simply connected.
I forgot simply connected. My God, that's like the most important assumption. Simply connected. Thank you. Simply connected. I'm going to put an underline even though I ran out of space there. Simply connected, yes. So there's our conjecture, and now let's unpack what that means using our extra bit of technology from BunG. So what that will mean is GK mod GA is gamma in the Delic double quotient. Okay, and this right here is equal to, by the way we rigged it, t times 1 minus b minus the degree of L times sigma 1 over d over L
What is the, on the second line, you have the power of Q.
yes.
And so what is the exponent that begins with what?
That is a d. Sorry, my circle fails. D times 1 minus
Oh, yeah,
d
with the
minus the degree of
But
one above.
actually-
Oh, one above. That is my God, I'm so sorry. D is like the hardest letter in the English language for me to write. It's, I never can quite get the L to just kiss the line, just kiss the circle. But yes, that was hideous. I apologize there. So what we're doing now is we're basically comparing. So the Tamagawa number is going to be it's going to be equivalently mass of BunG times the mass of the integral Adels, right? So we're just going to write out the equation in full, and this is an equivalent form of the Tamagawa number conjecture now. So this is unpacked. In other words, now using our bit of stacky magic. Have 15 minutes to discuss the real meat and potatoes. We have the equivalent of the conjecture is absolutely the number of levels. Kappa x g kx equals q to the e 1 minus g minus day L sigma. So of course, the mass, this right here is simply the mass of BunG. Of course, this can be written as BunG x FQ 1 over P. So what are we saying? This particular product over all the closed points of x will equal the mass of BunG. This actually gives you the last sort of one of the critical insights into the proof. That what does BunG of a curve look like? It looks like a continuous product of BGs over the curve. The order of this is all sort of weighted BG. So this is the idea that one's going to actually formalize in the case of the in the case of the Gaitsgory and Lurie proof, and this is what you'll be able to prove this formula easily. So again, this right here are sort of the orders. These are the sizes of the residual germs of BG, plus some kind of dimension, some kind of factor of Q, normalizing factor, and this is the mass of BunG here. So notice, by the way, a couple of important things. One, it is not a priori clear at all that either side converges. Both can be infinite sums, and they are infinite sums. In fact, it's not even clear when I've written out in the one case that the product converges. It should follow from the Veil conjecture / account of the Harder-Narasimha infiltration, but even for SL2, where it's like very, very explicit. So I got stumped. So let's see. What I'll do is I will post the notes of SL2 computation, which comes next, rather than go through them, because I didn't even manage to finish them. And if someone can find the error / complete the computation, I would be very, very grateful. But you can now very explicitly compute this. You can find out that this is a nice rational function in Q, and this side is some disgusting product where you have to count the number of everything gets to the power of the number of irreducible polynomials of degree D, and then it's multiplied in these rational functions. It's very weird. I've not been able to work out. So assuming Gaitsgory and Lurie are correct and that my reduction of the work is correct, it's true, but I wasn't able to do it directly in the one case. So that already shows that this is a highly sort of subtle thing. So all right, so now we're just going to, but what we're going to do now is we're going to cohomologically.
Did you do like x equals P1 or something?
So yes, P1 and SL2, and I just got this side is absolutely killer. So it'll be posted, and someone please tell me what the right computation is, because I thought that would be such a nice thing to have a really explicit example of this. And it just turns out that even in the simplest, SL2Q, you can't, SL2, you need to know Fourier analysis, or in the case of P1, you need to know, I don't know what you need to know, I haven't done it yet, but you need to know Gaitsgory and Lurie's entire argument, apparently. So, okay, so this is equivalent to, every time I'm rephrasing the conjecture, I'm just going to give more, I'm going to write conj every time I write these. Okay, so now it's looking really kind of plausible here. This extra factor, turns out to equal exactly the dimension of BunG. So this is very pretty. So this means that in both cases, we're dividing by q to the power of the dimension. Now in this case, if it's BG, the actual sign will flip. The dimension is negative what we expect. So this is actually still the order of the mass of the stack BunG divided by BG x plus 8 times its q to the power of its dimension. So as I say, you think of BunG as a BG fibration over the curve. And you start to see a kind of continuous product of all the BGs of these local BGs, BG kappa x's over the curve, and that gives you some sort of visualization of what's going on here. So this is equivalent, and now, whenever you want to have some computation of the I should say FQ. It's the computation of the number of rational parts, and this also is a computation of rational for a varying residue field. So, of course, now the hope is we can use Lefschetz trace formula to compute this mass here. There's also some. So now we have the following. Let's see. I'm going to skip ahead a little bit because I want to get the version net. So. Whenever you divide by the q, some factor like q to the dimension, that means that you're actually taking not trace of the geometric Frobenius, but you're taking trace of the arithmetic Frobenius. And so I'm not going to go through that computation again. That's in the notes. But the way you can now cohomologically reinterpret this using Lefschetz theory is as follows. So we have conjecture A. Lefschetz fixed point theorem. Lefschetz trace formula. Artins for BunG, Artin stacks in general. And that is as follows. This is sort of assuming that what's true for schemes was proved by Grothendieck for schemes and transfer here, which is over q to the power of dim BunG so phi means Frobenius. That's small, so don't make too much space. Acting on the normal, not compactly supported cohomology groups. Sorry again for my terrible board work and running into space there. So, assuming that we can generalize the Lefschetz fixed point theorem to stacks, this should just be true automatically. This is giving a point count of, this is giving a sum, an alternating sum of arithmetic Frobenius on the cohomology groups of BunG, and that should end up equaling basically the point count divided by q to the power of the correct dimension. And so this will just follow from Lefschetz, and this was proved by Kai Behrendt as part of his PhD thesis. A quick mention on how it's done. You have to use two spectral sequences. The first spectral sequence you have to use is to establish this kind of Lefschetz fixed point theorem, a Lefschetz trace formula for quotient stacks, which takes the form x mod g. When you do that, you end up using the Kovar sequence, the Kovar spectral sequence, and that gives you actually quite cleanly the sort of result for x mod g. But then, of course, that only really works if X is a quasi-compact scheme and G is kind of algebraic group acting on it. And as we've seen many, many times, BunG is not a quotient of a quasi. It's not a quasi-compact. It is not a quasi-compact stack in any sense. There is no surjective map from a quasi-compact scheme to BunG. And so you actually then have to sort of filter BunG by the so-called Harder-Nara-Simon filtration, which is equivalent to what Emerson was talking about in his class, which are these level structures. And then you have that filtration, or that stratification rather, then gives you another spectral sequence, which you can then use to bootstrap to BunG X. So those are the two processes of proving conjecture. Again, what happens here on the right-hand side, this is not a priori a finite. It's never a finite, but it does converge, more or less because, well, I think that's probably you can actually do the sizes of these particular traces of rays, the fall and phase conjecture stuff. The reason the right converges is because, or sorry, left converges is because the Harder-Narasimhan filtration automorphism groups grow really, really quickly. They're cubist and large now. So that's a quick little, hand-wavy outline of the two different things that go into this group. So that was already done. And now comes the much harder and more interesting thing, which we need some like topological insight. And I'll discuss the three methods in overview, and then we can we'll flesh them out over the course of the quarter. So conjecture B is that this alternating sum brings arithmetic Frobenius on HI, there's a typo in my note, BunG X tensor bar L equals this crazy product that we've seen up here. There we go. So this one follows from just upgrading algebraic geometry to stats. This one you have to be really clever. And again, you have to think about what's actually this sort of implying spiritually. And again, this is the idea that somehow these cohomology, the global cohomology, there's a kind of local to global principle. That these local factors all just sort of multiply together. It's a continuous product of all these local factors that give you these sort of global cohomology of BunG. So let's now, in the remaining 15 minutes, just do some pure topology, so topological inspiration. So for the moment, whenever you want to do topology, I think you should probably actually let yourself be over something like R or C. In this case, we're going to work over C. And so X is a compact Riemann surface. I'm going to briefly describe the sort of way in which Atiyah-Bott considers this. So it turns out that if G, since G is simply connected, any G torsor over X is trivial in the smooth category. So what that means is that if you want to think about how you would parameterize G torsors over a curve, you start with a trivial G torsor, which you only think of as a smooth structure, and now you vary the D bar structure. Idea, vary the D bar structure. So that's varying the complex structure, but of course, in doing so, you're overcounting something. So let's be a little bit more careful. This is a sort of Hodge theoretic approach to the problem. So let E smooth G times X. everything's over C here, but we're only thinking of these as kinds of real manifolds for the moment. The tangent bundle of P smooth is a G equivariant G torsor on X is a G equivariant vector bundle on X. Which implies we may write it as pi pull back E over X vector bundle. So we have
This applies.
a pi, I should say pi mapping E to. Oh, pi. Yeah, okay, so we have E over X as a vector bundle, but pi is, we want P smooth mapping for pi to X, right? Yeah. That it's the structure map of P smooth, I should say. Where did I declare my P smooth G times X? So we have pi mapping to X being standard projection. Okay. So we have exact sequence. Where EO is the adjoint bundle. And what you can see from what this buys us is basically the ability to see how we can vary the deep del bar structure. So what we're going to do is we're going to parameterize. So this is a priori a complex vector bundle. This comes as a complex vector bundle for free. This comes as a complex vector bundle for free. What we're going to do is we're going to find the extensions of this form. In which E has a complex structure, and this is an exact sequence of complex vector spaces. And let's call the space of complex space of such complex extensions. It is a torsor under the space C bar Tx0 of bundle maps. So these are C antilinear maps from Tx to E0. You can check that this is actually a torsor. This is a gigantic affine space. It's an infinite dimensional affine space, which implies that omega is contractible. All right. So let G equal the automorphisms of the smooth bundle. This is all bundle automorphisms of P smooth. Then BunG X is isomorphic to this huge, massive affine contractible space modulo the action of G, which sort of figures you're varying the D bar structure, and then you're sort of replacing all the trivial reparameterization where you conjugate by some smooth map. So what does this mean? In particular, the homotopy type a BunG is B curly G. This is called, by the way, the gauge.
Sorry, how do you define omega? I missed it.
Omega, yeah, I said it, I didn't write it on the board. Omega is the space of complex of extensions E such that this becomes an exact sequence of complex vector spaces. The space of complex structures on this fixed map, right, that you can place on E such that this becomes an exact sequence of complex vector spaces. And it turns out basically once you picked one, everything else under sort of standard cohomology is just a sort of difference between it and a C antilinear map from Tx to E naught.
And that's the Atiyah sequence, right?
Is that called the Atiyah sequence? I actually don't know. Is it this called the Atiyah sequence? That makes sense. Yes,
Yeah, then it's the Atiyah sequence.
This is the actual, yeah. Okay, brilliant. I didn't actually know that. It was, they didn't say that in the Lurie notes on this. Yeah, so this now gives us, of course, the problem with this is these are all massively infinite dimensional, but these things do exist. Topologists have constructed massive infinite dimensional things without any problem. So now there are three ways in which this, and now we have 5 minutes left, but okay, so we'll give yeah, there are three ways you can then basically compute this. You can basically understand this object. And these are all somewhat classical. And I'm just going to mention the three and maybe give a 1 minute summary of them and call it a day. So the first is rational homotopy theory. So Quillen's rational homotopy theory. Two is factorization. Say, two is we compute H homology BG Q via factorization homology. And then three is we compute the homology of BG, coefficients of Q, via factorization homology. And then appeal to a non-abelian, this I think is again due to Lurie and Gaitsgory, Poincare duality. So what is done in Gaitsgory-Lurie's article is they compute the analog, they come up with a sort of L-adic version of non-abelian Poincare duality, and they use this to sort of reconstruct an algebraic version of the graded. So what does Quillen's rational homotopy theory? It produces this miraculous graded Lie algebra. And so they go from sort of 3 to 1 to the algebraic version of 1. This miraculous graded Lie algebra that exists from Quillen's rational homotopy theory, they compute the action of Frobenius on it. And that allows them to show conjecture B. So that in broad outline is the way that the semester will proceed. So we'll have to fill in the various ingredients of conjectures A and the various sort of algebraizations of these. I haven't defined factorization homology, but that will be one of the things we'll come to, and I think we've already covered it in previous quarters. So it's something that we'll see again. So this is only the coarsest outline at this point, but this is where the real need of the argument occurs. So with that, I shall conclude. Thank you so much. Questions, comments, concerns?
So One thing, is the mass formula supposed to be related to the Tamagawa number? Are there implications or?
Yes, so I remember I had the well, so for unimodular groups, I think it basically is a special case. A slightly more general thing that takes into account that pi1 will give you the general mass formula, which you can always reduce it in the case of a function of over number fields by just appealing to a cover of the group that's interconnected. So I think it's not too much of an issue. But yes, the Siegel mass formula is just a special case of Tamagawa number equaling 1 in some sense. What it basically means is that there was that so you had the adelic, the quotient of the adelic volume of the adelic space divided by the integral adels, the volume of the integral adel points. And everything is basically what it says, that everything is contained in the integral adel points. That's where you get the product of the CPs, because you have to do it from each place. So the product of the CPs comes from the numerator, and comes from the denominator, and the numerator is just 1. So the idea that those two are equal is equivalent to the automorphic space having the Tamagawa number 1, Tamagawa volume 1. Yeah, I apologize. I sort of erased it right after I sort of struck it with my eraser right as I realized that's exactly the thing that's referring to. Question.
You said it was proved in Barron's thesis. Gaitsgory and Lurie like cite that, or did they do something?
So Lurie says that this was basically the argument was more or less following Barron. I think they've improved it a little bit. I think it's a little more streamlined. And they probably also the other thing is, and I should just mention this as a heads up, infinity categories are absolutely necessary for this because everything here is done at the level of chain complexes, which is like clearly the right thing to do for all of this. You descending somehow, if you use derived categories, you're forgetting too much information. You really do need the actual chain level complex chain complex computations for these things. So for instance, I think therefore they could really cleanly do some of the stuff by just appealing to homotopy colimits, which Barron couldn't do. He's very, very, I remember back in the day when I first reached out to Justin with this, trying to learn BunG. He said, no, you should just learn it. I was like, should I read Barron's like long 60-page paper on LN sheets on stacks? And his response is, no, you'd probably be better by just reading higher Topla's theory or higher algebra. Like you might as well get the formulas in right if you're going to do it. If you're going to invest all the time and energy. It's like otherwise you have to do quite a lot of work that you then just forget about or throw away. But yeah, for our purposes, everything here, this is the rational homotopy theory is not just a homology theory. It actually is. It's true that the H star, the total homology of a group has a co-commutative Hoff structure, but you can actually lift that to the level of the actual complexes, and that's the sort of miracle of what happens with Will rational homotopy theory. But yes, you're probably
just a comment about like why the derived stuff is even more important here than in previous quarters, because like we'll also talk about factorization algebras as like redo that, even though we've done it previously, and it's because last quarter the factorization algebras that appeared were all sort of classical in nature, right? It's Kac-Moody factorization algebra, whereas the factorization algebras that will be relevant here will be very much like derived factorization algebras. So we really need the.
It's by the way, just this is a very good source. Gaitsgory Lurie's book or Lurie's lectures or the abridged version are a very good way to learn. Like he does a beautiful overview and shows how it's, and it doesn't make it seem at all difficult, and nor is it hand-wavy, which is one of the issues because I don't know. I found a lot of people said okay, up to coherent homotopy, and what does that actually mean? He just at one point he writes it like this is what the higher coherent homotopies are. They're somewhat cumbersome, nasty formula, but yeah, I guess it's not quite the univalent idea that you should have no formulas whatsoever, but if you're like me and you're still worried and you're still firmly stuck in set theory land of Cantor-Dedekind, it's really nice to know that you can write these things out. It's like structured sets in the right sort of way. So it's a very readable exposition. And anything that was confusing here, I'm sure you'll be able to find. Well, the number theory stuff was amalgam, but everything in the second half you can find done much better by Lurie in his notes or by Gaitsgory Lurie. Their big book together. So.
Any questions?
Conjecture conjectures.
These were part of. So firstly, if you can conjecture A would follow by any reasonable definition of what the terms mean, right? Because that's what it has to be for like a computation of fixed points of stack. So conjecture A was more like, we're gonna work out the formalism. Yeah, I mean, there was something to check non-trivial, but
The concept is more the convergence. right?
yeah, that's true, that's true. So I guess that was actually, really, there was a thought, I will say this, and apparently Darren in his thesis says that Deline had a question on this. So you could say it's Deline, it's as old as the Lefschetz trace formula and the invention of stacks. And then this, of course, that makes it automatically equivalent to the Tamagawa. Conjecture B is just the Tamagawa number. So breaking it up into that particular form is, doesn't buy you much extra. Though the important point is like the actual geometric interpretation of this is kind of like the analog of a continuous product over the points. And the way you get it, that's through factorization homology. Factorization homology really allows you to talk about this, fibering things over Raman space in which points just collide, finite collections of points. And the contractibility of rational maps allows for so those are the ingredients that and they're called 1 and 2, not A and B in the original in the Lurie notes. They're called 1 and 2 because I had 5 or 8 sections in my talk, so I thought I've already overused numbers. So I have Latin numbers, I have numbers, and I was like, all right, we're now using letters. So next time I'll use Hebrew letters or something. Exhausting. I only know Aleph though. That's the problem. It's the only one that's using math. I would be a very short list. I presume
Yeah,
the next one's
I
gotta be
send you
some
an
kind of.
email with the
It's
next
gotta be some
week.
kind of beta.
Yeah.
What is the next one?
Bet.
That's okay. No. Aleph Bet. Who would have guessed, huh? Any other questions, comments? Otherwise, you're all free to go. Thanks so much for coming.
Thank you, speaker again. Sorry, I figured out.